it's going to is to remind me. What I noticed in your Edpuzzle answers about what is decay is that a lot of you are telling me about decomposition and how things break down in terms of organic material. And this is a little different because even though it is changing to a different form, it isn't disappearing. So decay in this sense, matter is always going to cycle. And so I want you to understand that it's emitting some sort of energy and particle to become a more stable state. Okay, and so this idea of decay, that was the definition I was looking for, not just the breaking down.
Some are thousands of years. If you look at this graph, we start with a 1 gram sample.
Right, how much of the sample remains after 1 half-life if you have a 1 gram sample? Right, I have 22 or 26 of you, 23, 3 more of you. Get back to your computer, press something. There we go, 1 more of you. All right, 5, 4, 3, 2, 1. We're moving on. Yes, it was 0.5. That would be half.
We're left with half of that, which is 0.5. After a second half-life, it's 0.25. After a third half-life, it's 0.125. And after a fourth half-life, it's 0.0625. So you're dividing that sample by 2 every time. So the equation is the number of half-lives is equal to the total time passed divided by 1 half-life. You could also write the equation to say that 1 half-life is equal to the total time passed divided by the number of half-lives.
So when they give you a question about half-life on the test in May, it's going to give you 2 of these 3 things, and you're going to have to be able to rearrange the equation and figure out the one unknown. So there isn't anything real challenging about that, but you do need to kind of be aware of how to do that, especially from a graph. That is the direction all your tests are going, is to be able to read graphs and charts.
Depending on what the question is asking. So for example, if we have a 44 gram sample with a half-life of 13 weeks, how much remains after 52 weeks? So we're going to take 52 weeks, which is the total time passed, and divide it by 13 weeks, which is 1 half-life, and that's going to give us 4 half-lives. So we have to put this 44 gram sample through 4 half-lives. So after we divide it by 2, we get 22.
All right, so how much is left after the second half-life? So you started with 44 grams. Half-life is 13 weeks. How many is going to be left after the second half-life? Don't know why my cat thinks it's starving. It's not. Okay, I need 2 more of you. Shh. 5, 4, 3, 2, 1. I see Heather's doing it in the box. Okay.
2 grams. Put it through a second half-life and we get 11 grams. Put it through a third and we get 5.5 grams. Put it through the fourth half-life and we end up with 2.75 grams. And that's your answer. You end up with 2.75 grams left of that 44 gram sample after 1 year.
All right. So that is it, kind of just the very basics. If you are struggling with this concept of radioactive decay and half-lives, if you go under no due dates, it'll say optional Edpuzzle videos, and it has a whole bunch of them, I think like 5. So if you're still struggling, make sure that you're going and kind of going through some of those. If you guys could travel back to your stream page, we are going to go go to the classwork tab. Oh, reminder too, if you scroll, if you're at the very top, the answers to 1 through 20, page 61 for practice, that cover the first 2 chapters, unit 1, are up there for you to check your work. So we're going to go to classwork, go down to this week. click where it says half-life of candium, radioactive dating, and open up. That should prompt you to make a copy for yourself. So each of you need your own copy, even though you're going to be sharing data and kind of working in these really big groups. Once you have this up and renamed, and you have your supplies, if you have your supplies are ready and you have them, if you could put a green check mark again, then I will know how many of you have supplies and are going to be able to physically do this activity and share some data with the others. Jason said yes. Okay, anybody else? I see Addis, it looks like, Gavin, Heather, Jason, Jesse, Lorelai, Mina, Shivan, Thomas. Anybody else have their Skittles, M&Ms, or pennies ready to go? You're gonna do the experiment yourself, but what you're going to do is shout out your data as you do it, so that people who don't have their supplies still have data to work with. And the more data we have, the better our curve will look. Yes, and you don't have to physically, you're right. If you found an online app that you want to use instead, that will work. There's lots of randomizers. Oh my gosh. So you can look at Jason provided if you don't have your Skittles, M&Ms, or pennies. And Laura has one too. That's not quite as long. All right, so let's talk a little bit about this. When you get into your groups, based on whoever's the oldest, will go first and read the discussion paragraph. And then the second oldest will read this background information. And then the third oldest will start on the procedure. And then so on. So you guys can take turns all the way till you finish step 5. What I do want to talk about, though, is a misconception that this lab can lead to, which is after you shake these up, and we'll watch a quick clip about what this would look like, is that you guys tend to, if it flips over and now it's decayed and it's emitted its energy, it's emitted a particle of some sort and went to a stable state. And then I always have you guys like eat it or whatever. It's not really gone, right? There would be a replacement for what it was now. That is, what you're eating is pretending you took on that beta particle or that energy, and then you replace it with like a dried bean or a dried pea. So it's one part of this activity I haven't liked as well, in terms of I don't want you getting a misconception that anything disappeared. Matter is cycling, energy is flowing, but nothing's suddenly disappearing. So that's what you're going to read about kind of in this procedure part, is replacing those with some sort of dried pea or bean to represent that stable product. Let's see. Oh, so I'm going to go to your week at a glance, just because I know that that's where I put the really short demonstration, and I regretted not showing this to first and third. And I try to fix things. So if you notice, they got to a point where it's 0, 0, 0. That is typical, but I still want you to run it to 10 tries. So if you look at go back to your assignment and go to the chart, you'll see that it has you doing this 10 trials. And yes, a lot of times you're going to get to zeros at the end, and that's fine. So the people who have supplies, when you get in your groups, are going to be shaking and shouting out these numbers to fill into the chart. Okay. And then if you don't have supplies, then you're just making sure that you have a record of some data so that you can do some data analysis once we get to that step and then start plotting it. But what I'm going to have you guys do, I'm going to come in and out of your breakout rooms to listen to you reading the discussion, the background, and the procedure. I will tell you that the one thing that students forget to do that is just something I want you to add in. Where did it go? It didn't highlight. It's to start timing. So as soon as you decide you're ready to do your experiment, you're going to press a timer and measure in minutes how long it takes you to go from 0 to 10 half-lives. You don't have to do it for each half-life, like just one big span of time. So maybe it takes you 5 minutes and 30 seconds to get through all of this. And then you're going to divide by 10 to figure out your approximate half-life. So this is one place where usually if you were on teams, all of you end up with something very different, which is fine. I want you to kind of look at different types of numbers and different amounts of half-lives. Not to mention that most half-lives are like 5,730 years, or like these charts show you, they're huge, right? 1.3 billion years, and yours is going to be in seconds. So a big difference there, but I still want you to time it. So from start to finish. So that's it, but I will come around and ask or answer questions and be listening to you in your rooms and helping with that. We're going to do 4 rooms. They should be open. 98, if you can't find 2 more. Yeah, go ahead. The reason why we do 100 is just for calculating fractions, right? It makes it a little bit easier, but you don't have to. You can do any, you could actually do any number as long as you take the fraction of your original parent. Leo, you're in room 3. Leo, are you engaged in class or are you somewhere else?
It's our website. Oh, I see. All right, so it looks like no one needs the data, so I guess we can just go our own ways then.
Yeah.
You guys could actually average some data and get much better curves.
Yeah, we could do that.
So then we do our experiments and then average it, or put the averages in our tables?
You could do it either way. But if you graph the averages, you will get a much nicer curve.
Let's go. I found 2 more coins in my room, so now I have 100.
See. All right, so do we want to?
Hi, Miss Roberts.
Yeah.
So, are we having one person do the experiment and everybody else takes their data? Or does everybody do the data, and if there's somebody who doesn't have like M&Ms or Skittles, they just copy from someone else?
Yes, so the second one. The other thing that we normally do is your numbers and your graphs are much better if you take averages and kind of Just like with flipping a coin, if you only do it 10 times versus 100 times, this provides you a chance to do that as well. But it's
So,
so
like, you average like out of everybody in the group, or average
right, like everybody in the group, like record your own individual data just to show that you did it. But then if you want to use your averages on your graph, it'll look better.
Okay, I don't know. Yeah, we'll see. All right, thank you.
Uh-huh.
Okay, guys, so
Okay. I think, yeah, we need to make sure that everything is facing up, I think. Because the next step is to shake the cup. I'm gonna do that now.
So we just do like the flipping coin things, right?
Yep. And then after everyone's done, then we'll average them and then do the graph based off that table.
Tommy, did you get the second point?
Okay, 4. Yeah, it divide by 2 again.
I'm confused on step number 3. So I got 48 Skittles with the S side up. So do I just put those back in the cup and then shake them again?
Yes. Are you removing the ones that aren't?
Yeah, I've removed the ones that didn't have the lettering.
Yes. So then, yeah, you shake it up and do that again.
So I shake the ones with the writing on top.
Yeah, you could run this lap either way, as long as you decide what you want your parent atom to be versus your daughter atom.
All right, thanks.
Uh-huh. All right, welcome back. Welcome back, everyone. We're gonna talk briefly about these questions as a group. So have your Google Doc where your data is up and ready so you can also answer some of these questions. If you know the answers to some of these questions, write it in your chat box and on your Google Doc. And then we're going to play a quiz is on chapter 1 and 2. I'm going to close that. All right, let me open this up so I can see all of you, even though some of you have your videos on. All right, so I'm on the question part. I'm assuming, did anyone not have enough time to get all of their data points? Oh, now everybody's back. Did anyone not have a chance to get their data points? All right, I'm going to assume that is a yes. And everybody has something in this chart that's on my screen. Let me make sure I'm sharing. No, I'm not. There we go. So everyone should have some data on this chart. Before we do our quizzes, I just want to go through some of these questions. Some of them I'm going to let you answer on your own. But number one, the M&Ms in the chat box. What do the M&Ms or the Skittles or the pennies represent? What is that representing? Good. Anybody else? True? Yes. Good. Yes. So these are representing the parent atoms, your starting atoms. Okay. All right. Number 2 says the split peas. Like if you had dried beans or peas and you replace that during the activity. Good. So I see daughter atoms and decayed atoms. Yes, which are the same idea. The atom that happens after it becomes stable. Okay. And how much of a radioactive element becomes stable in a half-life? So how much of it? Yes. Yes. Yes, about half. That's the point, right? And one of the question came out yesterday was really good about spontaneous versus random. So we can't look at an element and say this atom is going to decide to become stable and release its energy at this time. But on average, there's half of them are going to do it in a certain time period. So that 5,730 years, just like when we flip pennies, heads or tails, about half the time you are going to get heads or tails. The same thing is applies to this. It's going to happen at a set rate, but we can't say exactly point at that atom and say it's going to undergo decay now. Okay, so we don't know which of those atoms are going to do that, but in a certain period of time, about half of them have. Okay. So number 4 is going to be done in seconds. So it says, according to the graph, what is the approximate time it took for the radioactive members to get to 1/2? So that'll be up to your chart and graphs. And then number 5, the rest of these, I want you to kind of interpret. There is, we're not doing years. We're going to be doing seconds on number 6. And then on number 7, I want you to assume they're talking about carbon-14. Okay, so number 7, you're going to work for carbon-14 since it says 2,000 million years. And then use this table and then show me that you can multiply 1/2 times 1/2 times 1/2. So you know how to multiply fractions. That's it. I want to make sure we have time to look at your knowledge of chapter 1 and 2. I am available through email, through Google Classroom, or during on-demand times if you have any problems with those questions. We are moving your biodiversity lab as far as it being due till after you have a chance with your team to talk and share all your photos and evidence. So everything takes about 10 times longer than what it does in the classroom. So we are going to postpone that so that you can work on finishing up this half-life document. We'll do the biodiversity get together next week. So this half-life thing is due Sunday. So we're doing this first to finish it, and then we'll get back to that diversity lab. You still should be collecting evidence and photos, but first and third said that some of them hadn't gotten their photos into their documents yet, and they hadn't had a chance to get to talk to their team about their data or evidence yet. So we will work on that next week to finish up. Yes. All right, we were going to start a live quiz. This is quizzes on your textbook, 458313 from both chapters 1 and 2. $17 of you. And I should have 28, so I need 6 more. 5 more. 4 more. 2 more. Let's check here. Leo, where are you? Okay, so Lorelai, just put your answers in the chat box. There's Leo. Leo, that's twice now. I'd like you to be near your computer. You're trying to get in? Okay, let's do it. Number 1 is number 1 right now. we're taking 3 of the cats. Gabe wanted to. It's up to you guys. Okay, she doesn't then talk to Gabe. Why aren't you in class? What? Class isn't until 10:35. It's 10:31. Number 1 is still number 1. Jason, go beat number 1. Tyler, there you go. Man. Let's say when I get questions. Why are you out of class? Right, we are going to run out of time. You have about a minute, and then I'm going to answer any questions for assignments. And then we're going to figure out who number 1 is so I can mark it. Okay. All right, let's look. So who was number 1?
Me,
Who was number 1?
me.
I'm going to mark down Isla for a treat and Laura Wayne for a treat. Mira. No one's. Who was first though?
Me.
It was Amelia.
Yeah,
Awesome. Nice job. I'll mark you down. Right. So you should be getting a nerdy treat in the mail as long as they seem to still keep sending them, even though I know I'm not supposed to send them with the parcel stuff in them, but that's okay. So far, they're not stopping me. All right. I'm going to go back to your week at a glance in this last 30 seconds. Let me know if you have any questions about this. If you are good, then it is advisory time for you. Otherwise, I'm going to hang out and answer questions until I load my advisory up. So, any questions? Thank you, Tyler. Woo-hoo. He told me stop recording.